Okay, so under ideal, supposed to be ideal. Under ideal mixing with the above assumptions, what do we get? This equation, which we've already discussed. Okay. Then now, using integration of the first order differential equation from time t is equal to 0 to t is equal to t. So you have to set the boundary conditions, t is equal to 0. We're told that the salt concentration in the tank equals 0, okay? Then at any time greater than 0, so where t is greater than 0, you have a concentration greater than 0. Okay, so CL is equal to CL, T is equal to 0, which is equal to 0, which is the same. So now using integration, we come up with this working formula, which you need to know by heart. By fire, by force, this one should be in your head. So we'll look at it a bit later as we go down and try and see how to use it. Okay. So this is outlet concentration as a function of time is equal to inlet concentration, and then you have the square brackets 1 minus exponential to the power negative f over v multiplied by t. Okay, so t is time. F and v, we are yet to see. We're still going to look at it. We're still going to use it. We're going to apply it so you'll feel better. Okay, so this is how our question looks like on a graph. Okay. So at t is equal to 0, what did we say happens at t is equal to 0? So from t is equal to 0 up to somewhere here, we have non-steady state. Then steady state comes somewhere here where you have change in concentration in the reactor over change in time becomes equal to 0. Okay. Then non-steady state also is achieved here now where you have dCA over dt is less than 0. Then again, you have steady state also being achieved here. Okay, this is why it's a combination of non-steady state and steady state condition. Okay, so after t is equal to 0, what is happening? This is your t. After t is equal to 0, it means that your change in concentration over change in time also becomes greater than 0. Okay, so for this period here, up to here. So what happens here? Let's try and understand this graph. So what is it that happens here that makes us change and go to steady state? What has happened here? dCA over dt is equal to 0. Can someone explain from what we've understood so far?
Can I try, madam?
Please try.
I think we're dealing with a tank here. And at this point, let's say we have reached a certain level where the concentration from what is being injected into the tank and what is in the tank, they are now equal at a certain period of time. They are now equal. So when we go beyond that, we find that maybe, can we say the concentration, there's an overflow there, where now we are getting into the non-steady state.
Okay. And then how is this steady state at the end again then?
Ooh.
Yeah, you're right. Yes.
Let me go back.
Let's go back to the example of Mazoe, isn't it?
Yes. Yes.
So you have a glass half full.
Yes. So as you are injecting your Mazoe.
Okay, let's say the water is full. Doesn't matter, isn't it? Let's say the water is full, isn't it, in the glass?
Yes.
Then now as you are injecting the Mazoe, you're pouring the Mazoe into your glass. that already has water full? What are concentrations like?
The concentration now.
At a certain time.
So
okay, let's say before you start pouring, that T is equal to 0, isn't it?
Yes.
So at T is equal to 0, what's the concentration of mazoe in your glass?
Since we have water, we may say there's less concentration of mazoe.
There's 0 concentration actually of mazoe.
Yes. So as we start pouring mazoe in the water, the concentration begin to increase.
To be greater than 0, isn't it? So dCA over dt will be greater than 0, isn't it?
Greater than 0.
Because from any time apart from 0, from T greater than 0, you have what? You have concentration of that mazoe ending up in your glass of water, isn't it?
Yes.
Over time. So dCA over dt is equal to 0. So that's now the non-steady state phase, isn't it?
dCA over dt is equal to 0. That will be steady.
It's greater than 0. That's non-steady state.
Yes.
Greater than 0, yes. 0. So now you're pouring your mazoe, isn't it? It's overflowing, but you keep pouring. So how do we get here? You say that we're going to get to this stage here. dCA over dt is equal to 0 when what happens?
When there's equal concentration of mazoe in the cup and from the source.
Yes. Yes. So that will happen for a certain interval of time, no?
Yes.
Usually a short one.
Sorry?
Yes. So now going forward, are you able to try and explain to us now what happens now? So when that concentration becomes equal, how do we return to non-steady state now?
The non-steady state, probably we again try to reduce the concentration. We pour water.
To pour water. Okay.
The non-steady
state. Okay, when there's an overflow. When there's an overflow.
Maybe let me try.
Okay.
In the non. Okay.
Someone said they wanted to try also. You can go ahead.
Yes, madam.
Yes, go ahead, please.
Yeah, so I was still looking at the example we've been given for the mazoe and the water. So now on dCA over dt is less than 0. Maybe my understanding is that the concentration of the mazoe, which we are pouring into that water, is getting higher than the concentration of the water. I don't know if I'm on the right track.
The concentration of the water. Ideally, we achieved that before that. Actually, we achieved that here at steady state. We even achieved the situation where we had concentration of the mazoe we were pouring from the bottle was equal to what was in the glass. I don't know if you've understood. So that, yes, you are right, but that's when we achieved it at steady state.
So at steady state, madam, I thought it's a point where the concentration of the mazoe becomes equal to the concentration of the water. Isn't it?
No. Not equal to the concentration of water. At steady state here, this steady state here, it means that the concentration of mazoe in the glass is now equal to the concentration of mazoe in the mazoe bottle.
Okay, madam. First, I'm trying to look at these to differentiate steady state from with respect to non-steady state.
Mm-hmm.
So when we have steady state flow, we're looking at there's uniform distribution of concentration within the tank itself. Now, when we have that non-steady state, meaning the flow in itself, it's not homogeneous, it's not uniform. So we have reached a level where we are saying the concentration of salt over time is less than 0 because of that non-uniformity in the fluid.
Okay, remember our assumption was that we say that it was homogeneous. It was a homogeneous distribution.
Yes.
So steady state, what defines steady state? Maybe let's come back there. Why are we calling this state steady state? Your definitions are a bit not correct, and they can be a bit misleading. So what are we calling it? We're saying it's steady state. Why? Because change in concentration of that salt over change in time is equal to 0.
Okay.
Okay, hence it being called steady state. The non-steady state, it means that that is not true. It means that it's either greater than 0 or
less
than 0. Those are the definitions of steady state and non-steady state.
So meaning here, what can lead us, because we had achieved the steady state, the concentration of salt over time was equal to 0. Now it's more like we are going below 0 now to achieve the non-steady state. What could lead us to that situation?
Thank you. You have brought us to where, that is what I'm also trying to find out from you. Actually.
Yeah. Is it that we are trying to inject more water in the tank again?
No, I think, yeah, I'm trying to understand also.
Okay.
Not really injecting more water in the tank, but that I think whatever you're injecting, like it's not changing in any way, kind of. I don't know if I'm making sense.
So look at the graph. Okay, look at the graph. Look at the blue graph, isn't it? So we're rising, right?
Yes.
Right? There's a positive value. Our gradient is positive, isn't it? So we're rising till we are constant here, steady state, isn't it? Yes. Then now we're dropping. So remember the y-axis is what? Concentration, isn't it? So from here, it means the concentration is dropping, huh?
Yes.
It's dropping till we achieve a new CAI concentration in the reactor. Then again, we become stable. So what happened here? What do you think could have happened here?
Could there be some production within the system where we say there could be some reaction happening, then something else is produced, which leads to lowering the concentration of salt over time?
Okay. What do others think?
I think I have the same sentiments, because if there is no change at all, and we are saying this is like a tank, meaning that I don't know if is there any outlet for this tank, or it's just constant? I mean, no form of...
No, there's an outlet. It's filling. So there's FL actually.
Oh, there is an outlet. Okay.
Remember, this is how our tank looks like.
Okay. Yeah, I think I would have the same sentiments that maybe at some point there is some production that is causing maybe some dilution of the salt.
Okay. Okay. Okay, working with what you just said, are you able to explain how we achieve a steady state given that here now? After that. Are you able to explain this steady state now here?
No. And no, I cannot, because the issue is, if there is production, meaning it has made, I mean, there is some dilution of the same concentration of salt. Then for it to be, as in the change of this concentration to be, I mean, with time to be constant again, no, I can't explain that, I think.
Yeah, it's possible. It's possible. We may achieve production to some level. To some level, that production, after interacting with salts at a specific period of time, that production stops and the concentration remains the same at that period of time. So it's possible to have dCA over dt equal to 0. I think with me it's possible.
Okay. So now let's assume in a case where we don't have, where production is equal to 0. How would you explain this? So remember, initially we said this work with production is greater than 0. But what if production is equal to 0, like we stated in our assumption?
Production is equal to 0.
How would you explain this drop in our curve? Which other way?
Can we look at the did we give an assumption to say the volume of the tank is fixed?
Yes, unless you want to come and weld part of the tank and increase. Usually the volume of the tank will remain fixed. That one will have to remain. Okay, let's continue, then we'll come back to this, okay? Let's continue with the question, then we'll try and see how. So from integration, we have this is a working formula, okay? So we'll come back to this also. Oh no, don't tell me that this question is not solved in these notes. Okay. Let me just quickly find a question in relation to this. I actually thought we had solved this one in the notes, but it's missing. Okay, just give me a minute to get a question, then we'll look at it together. Okay, I found the question. Let me just share the screen with you. Okay, just one moment. Trying to get rid of my old screen. I don't know what's happening. Okay, I'll be sharing shortly now. Okay, are you able to see my new screen there? It says question 7.
Yes, Doc.
Okay, so it's a similar question to that one. Okay, so the question says, visualize a newly constructed rectangular fish pond with 100 cubic meters volume filled with water from a borehole at a volumetric flow rate of 0.5 liters per second. Full stop. If the dimensions that make the volume to the spill over are 10 meters long by 5 meters wide by 2 meters high, suppose that when the water starts spilling, that is when the outflow starts at the same rate as the inflow, a micronutrient or pollutants, which is copper 2+, is dosed into the pond along with the inflowing water at a concentration of 3 milligrams per liter. Similar issue, isn't it? So you have a certain flow rates and you have a spillover, an overflow happening, okay? And when that overflow starts, a micronutrient or Cu copper in short is dosed into the pond along with the inflowing water at a concentration of 3 milligrams per liter. So the question says, making the assumptions, sketch mass balances, and give the working, the English was not very correct, and give the working equation. So making assumptions, sketch, and mass balances, comma, give the working equation. If the required level of the micronutrient is 1.5 milligrams per liter, how long will it take to reach the concentration and thus switch to 1.5 milligrams per liter copper dosing, okay, in the inflowing water to maintain the required level? Okay, so let me try and explain it. We have our fish pond, okay, which has a certain volume, which is 100 cubic meters. So remember dV over dt is equal to 0 in this case, because the volume of the pond will not change, okay? Then what is happening, this rectangular fish pond has been filled with water from a borehole at a volumetric flow rate. So this is our Fi, isn't it? Fi is equal to 0.5 liters per second. F inlet. Okay, so we've been given the dimensions of that particular pond. And we have been told that when the water starts spilling, what happens? Immediately it starts spilling, a micronutrient, which is copper, is dosed into the pond along with the inflowing water. So the concentration of copper being dosed into that pond is 3 milligrams per liter. Okay? So now we have been told to say, if the required micronutrient in that fish pond, the concentration that we are trying to achieve is 1.5 milligrams per liter inside the fish pond, how long will it take to reach that concentration? Okay, so remember T is equal to 0, okay? T in the terms of time for start the dosing is T, will be our T is equal to 0. It means that there's 0 concentration of copper inside the fish pond. Then at a T greater than 0, what happens? Our concentration in the reactor, which is our fish pond, will increase. Okay, so it will start from 0.00 something to 0 point something. Over time, till it will reach 1, until it reaches 1.5 milligrams per liter. So they're trying to say how long in terms of time will it take to achieve 1.5 milligrams per liter in your reactor. And now the aim is that once you reach 1.5 milligrams concentration within the reactor, you're going to switch your dosing of that copper from 3 milligrams per liter to 1.5 milligrams per liter for it to suit the concentration of copper in the pond. So you're trying to achieve a case where you have your CI equal to your C0, where it's C0, that is the concentration of copper in the reactor. Is the question clear?
Yes, we are following, madam.
Okay, perfect. We continue. So this is the steady and unsteady state problem data, right? So at least I'm happy that the first part of the graph we understand, isn't it? So as you are dosing, what's happening to your concentration in the reactor, it's increasing, isn't it? So our graph is rising, our curve is going upwards. Our gradient is positive. Okay, so this is a system that has both steady and unsteady state conditions. Consider a well-mixed tank with that. So it's basically, so at T is equal to 0, a solution of copper is continuously pumped into the tank as tank influent. And at T is equal to 0 also because the pond is full, isn't it? So meaning at this time also what's happening, there's also going to be an effluent also. Then and also at this time we have a reactor effluent is established and influent salt concentration is 3 milligrams per liter. The influent and effluent flow rates will equal, isn't it? Because there's overflow. So you have Fi being equal to Fl, which is equal to 0.5 liters per second. Okay, so you sketch the system. This is your always sketch. So if it's a test exam, you are always supposed to sketch because you get marks for sketching. So you sketch appropriately. So you have your inlet. Okay, forget the N here. It's supposed to be copper, so CUI. You also have concentration of copper multiplied by inlet volumetric flow rate as your input. Then you have what's happening inside your pond, and then you have the outlet, which is copper. It's supposed to be CUL multiplied by FL, which is our output. So here inside our reactor, what do we have? We have the CU0, okay? So this is that time is equal to 0. So copper will be equal to 0. Then you have your volume, which is fixed, okay? And your CU, okay, at a certain time, at T is equal to T, for example. Okay, so you have that place. So the initial concentration of copper in the reactor is CCU0, okay? That is at the time equal to 0, so this will be equal to 0. Then the concentration of copper, this is also a typo, copper in the effluent will be CCUL, which is the outlet. Okay, so mass balance equation, we looked at this. So what's coming in minus what's leaving plus production. Okay, what else do we know from here? We looked at this equation also. It comes out neatly like this. Hoping we've understood it also. Then one thing we know for sure is that dV over dt will give us 0. Production of copper will be equal to, for the nutrient, N. Maybe that one is representing nutrient. So that one will be equal to 0. So in that case, we have this formula, working formula here. Assumptions in the system, the reactor is ideally mixed, no production in the tank. Nutrient pollutant entering the tank is instantaneously and homogeneously. Okay, seems like I had gotten logged out there also. Let me just bring back the screen. Okay, so the assumptions, I think we ended here. Some of the assumptions are pretty clear. Reactor ideally mixed, no production in the tank. Nutrient entering the tank is instantaneously and homogeneously distributed. The nutrient concentration is uniform in the reactor. Therefore, effluent concentration equals concentration in the reactor. This one also is clear. Therefore, we can replace reactor concentration with outlet concentration. This one also we've discussed. I hope it's clear to everyone. Okay, so under these conditions, the ideal mixing, with the above assumptions, we come up with this. Inlet minus outlet. Okay, so this is the, remember the question, the formula I was saying this would be our working formula. Okay, so remember this formula here, that's what we're going to use here. Okay, so that is through integration of the first order differential equation from time t is equal to 0 to t is equal to t. So remember, what is the question asking us? The time, it's asking us to find t, isn't it? The time that it would take for us to achieve 1.5 milligrams per liter concentration in the reactor. So how long will it take to achieve a concentration of 1.5 milligrams per liter in the reactor? So from this equation, where is our time? Our time is here, isn't it? So meaning we need to make this the subject of the formula. Okay. So you multiply all sides here with natural log. Okay. There you have it. Because you're trying to free this. Remember, it's in a log, it's in an exponential there. So you first come there, okay. All sides of the equation should be multiplied by natural log. After which now you free your t and make your t equal to natural log of that multiplied by negative v over f. V is the volume we have given, isn't it? What about F? From what we've understood, what is F here? F is basically the flow rate, isn't it? We're going to move it from, initially we're given in what? In liters per second. So we're going to move from liters per second to meter cubed per second. So to do that, we're going to multiply with 10 to the power negative 4 for us to achieve that. Okay, and that is how this is achieved. T will be 1.6 days. So it will take 1.6 days for us to take 1.6 days for us to achieve a concentration of 1.5 milligrams per liter of copper in that tank, that 100 square meter tank, that 100, cubic meter tank, which we're calling our fish pond. Okay, so in terms of time, we found the answer there. Then let's look at the concentration. Remember, we were asked to say, to achieve this concentration, so meaning inlet and within the reactor becomes the same, isn't it? So meaning this concentration, we're going to put 1.5, okay, because we're trying to achieve 1.5 milligrams per liter. Okay, then what the dosing rates is known by, the dosing concentration for copper, we've been given in the question as 3 milligrams per liter. So we'll basically do that over the 3. So basically subtract that and divide by the dosing concentration here at the bottom. Okay, so like I said earlier, this is volume, so there'll be a negative sign here that you don't need to forget. Then you find our answer there. The second part of the question will be, what will be the concentration of copper after 2 days of dosing? What will be the concentration of copper after 2 days of dosing? Same formula, okay, except this time we're not being asked for time, isn't it? But we're being asked for concentration of copper in the reactor, isn't it? Are we together? Are we following?
Yes, madam.
Okay. So meaning, if we are being asked for concentration of copper in the reactor, isn't it? That's our main point of interest. Meaning we're being asked for what? Which is the same as the outlet concentration, isn't it? So our CLT will remain as in the formula, isn't it? Then the inlet concentration is 2 to the 3, okay? And then what else do we have? That formula, isn't it? So 2 days of dosing so you get 2 days and convert it to seconds. Okay, we're working with seconds here. So 2 days into seconds gives us 172,800 seconds. That's what we multiply here. So we have our volume there in cubic meters per second, our volumetric flow rate in cubic meters per second, divided by the volume of our fish pond. Okay, exponential of that value, which will give us 2.5 milligrams per liter. Okay. And the third question here says, presume the inflowing copper concentration is not adjusted after reaching 1.5 milligrams per liter in the pond. So they're trying to tell you, forget about that target of 1.5 milligrams per liter in the pond. Forget that. Let's assume that they did not adjust the concentration after they reached 1.5. How long will it take to reach the 3 milligram per liter outflow? So again here, what's the issue here? Time, isn't it? How long? It means time. So same formula, except this time we are supposed to make T the subject of the formula like we did at the very beginning, where we multiply both sides by a natural log, okay, and so for T there. And so now it says, how long will it take to reach this outflow? So it means that you have your dosing rate, isn't it? 3 milligrams. And they're telling you how long will it take for you to reach there. So what they're asking you is that you just need to find a value just before 3. Okay. So in this particular case, the value that we picked, the closest just before 3 is what? 2.99. Okay, so 2 decimal places is enough. 2.99 minus 3 divided by 3. So that is in seconds. So when you convert that to seconds, you convert that to days from seconds, it will give us 6.6 days. So this means that maintaining the same flow rate of 3 milligrams per liter, it will take 6.6 days to achieve a flow rate, to achieve a concentration of that copper in the fish pond, which will be the same as the concentration or the dosing concentration of copper into this fish pond. Any questions here?
I think after class we'll try